All right, we begin one of my favorite sections of pre-calculus because, as you know from my algebra classes, I like solving equations. And that's what we're going to do now. We're going to solve equations. They're going to be trig equations. So instead of x's and y's, there's going to be sines of thetas and cosines of thetas in them. But we're still solving equations. So I'll show it on the screen too. So all those steps and stuff, that we would do are kind of similar, right? Where, but instead of getting rid of the little x, maybe there's a cosine theta on both sides. We'd have to get rid of the little cosine theta. And instead of getting x by itself, we get the cosine theta by itself in some instances. And we'll work different types of equations that involve trig ratios in them. But solving equations, you actually get an answer. It's not so much making two sides of the equal sign match. It's actually finding out what is theta for this problem. Also, you get to work on both sides. Since we're not trying to make things match, you can work across the equal sign like a conventional equation and all of that. So next section of your notes, solving trig equations. Solving trig equations. If you put this down, we are finding the degree or radian values for theta. We are finding degree or radian values for theta. I generally do degrees, because why would I want to do radians, right? But you could do radians. And again, just mentally preparing you for a possible college course, something like that. You take college trig, they may want radian answers for some reason. We'll generally do degrees here. You get to work both sides, as I mentioned before. I'm going to jot that down. You may work across the, in fact, you'll have to usually work across the equal sign. And the key to solving regular equations is get x by itself. Well, here's your key. Isolate the trig function. Isolate the trig function. That's your usual key to solving these. Of course, you remember back to Algebra 1 and Algebra 2, they're all different kinds of equations we'd solve, so sometimes there'd be special steps here or there, but for the most part, it came down to getting the x by itself, or in this case, getting the trig function by itself. So write this down in your notes if you would. 2 times the sine of alpha is equal to the square root of 3. We want to figure out what alpha is equal to. Well, my key is to isolate the trig function. Well, right now, the trig function isn't isolated. There's a 2 with it. How do I get rid of the 2? Divide it away, right? Just like if this said 2x equals 5, I was going to say 5. Well, dang, that works out to a fraction. I hate fractions. 50. All right, then we divide both sides by 2, right? And x equals 25. Well, here I divide both sides by 2, and now I get the isolated sine alpha equal to the square root of 3 over 2. You're doing this with me there at your seats. Once you've isolated the trig function, the next step is to ask when. When does the sine opposite over hypotenuse equal square root of 3 over 2? And for this, you use your special triangles.
30 degrees. 60 degrees.
60 degrees. The opposite is square root of 3 for a 60, right? The hypotenuse is going to be 2, but for 30 or 60. The opposite is square root of 3 for 60. So we know that at least I have a 60-degree reference angle. But write this in your notes. We are going to use ASTC to determine possible quadrants, and we're going to list all possible answers. So use ASTC to determine possible quadrants, and list all possible answers. You'll notice here that there's an understood sign, S-I-G-N, in front of my square root of 3 over 2. What's the understood sign here, class?
Positive.
Positive. When is sign positive?
Quadrant 1 and 2.
Quadrant 1 and quadrant 2. Which means I'm not going to have just one answer for alpha. I'm going to have 2. I'm going to have the 60-degree angle that's in quadrant 1, which is, of course, 60 degrees. But I'm also going to have the 60-degree angle that's in quadrant 2, which would be 120 degrees, right? Because you come off the x-axis up 60. 120 degrees has that reference angle of 60. So there's 2 answers for alpha. My quadrant 1 answer and my quadrant 2 answer. The sine of either of those would be the square root of 3 over 2. Does that make sense? Write this one down. Cosine, or 3 times the cosine of theta is equal to the square root of 2 plus the cosine of theta. 3 cosine theta is equal to the square root of 2 plus the cosine of theta. This is not too different than having something like 3x equals 7 plus x. You have an x on both sides. We can't have an x on both sides. I said get rid of the little one. Well, which of these is littler, a 3 cosine or a 1 cosine? 1 cosine. So get rid of it by moving it over as a negative cosine theta. That's going to give me 2 cosine theta. The line here was not a division symbol, by the way. I was simply marking the cosine thetas. 2 cosine theta equals the square root of 2. Now we isolate the trig function by dividing away the 2, just like in any ordinary equation. And I'm going to get that the cosine of theta equals square root of 2 over 2.
45 degrees.
Well, to figure out what alpha or what theta is, I need to figure out when is cosine square root of 2 over 2. And Chris, you said at?
45 degrees.
That's my reference angle. But notice it's a positive. When is cosine positive, ASTC class?
1 and 4.
1 and 4. So I need the 45-degree angle that's in quadrant 1, 45 obviously, and I need the 45-degree angle that's in quadrant 4.
315.
315. 360 minus the 45 gives a 315-degree angle. And so if you were to put a 45-degree angle or a 315-degree angle in for either of these, it's a true statement. The equation would check for those 2 possible answers. Does that make sense? Write this one down. 1.5 plus the sine of theta is equal to 0. 1.5 plus the sine of theta is equal to 0. Again, we want to start by isolating the trig function. What would I have to do to isolate it, Jamie?
Minus the 1.5.
Yeah, or move it over as a negative 1.5 to get that the sine of theta is equal to negative 1.5. Or you could say negative 3 halves. Maybe easier to think of it that way. Well, when is sine 3 over 2? Opposite over hypotenuse.
Sine. No, it's 30. I don't have.
Wait a second. A leg is bigger than the hypotenuse? No. In fact, remember, we said sine goes from negative 1 to positive 1, remember? That's the limit. It doesn't go past that. That's not an answer. There is no solution. And so remembering some of those limitations that were on the ranges. Now, tangent, cotangent, it can be anything, right? For instance, if this had said tangent of theta, well, when is tangent opposite over adjacent negative 3 over 2? Well, it's not a special triangle, is it? There is no leg of 3 and leg of 2 in the same triangle. So here's where you have to get your calculator out. And we're not going to have very many of these, frankly, because we primarily want to use the special triangles. But here we would have to take the arc tangent of negative 3 halves. And what do we get when we take the arc tangent of negative 3 halves?
56.3.
56.3 degrees approximately, actually negative 56.3, but take that negative back off. That's your reference angle. When is tangent negative? What 2 quadrants? 2 and 4. And so you would take the 56.3 that's in quadrant 2, and you get 123.6 degrees, or 0.7 degrees, whatever, I'm sorry. And the same thing in quadrant 4, which would be 303.7 degrees. And we'll occasionally use our calculators, very rarely though. Usually what we're going to be dealing with are those special angles, where we have 0, 30, 45, 60, or 90 for the reference angle. But it is possible, like I said, we had sine. It fell outside sine's possible range, no solution. Does that make sense how we got no solution there? And again, if you think through opposite and hypotenuse, leg can't be bigger than hypotenuse. But what if there's multiple trig functions? Like, for instance, cosine theta, cotangent theta equals another cosine theta. I'll tell you what a temptation is. Students like to say, ooh, let's divide away cosine from both sides to get cotangent equals 1. Just one problem. If you ever divide away a variable, you lose roots. Let me take you back to this thought. Remember when we had a quadratic like x squared minus 3x equals 0? And some go, oh, let's divide everything by x. I said, no, you can't do that. Instead, we would factor out the x, leave ourselves with an x negative 3, and we get 2 answers. X equals 0, and this x would have to equal a 3, right? So write this in your notes if you would. If there are multiple trig functions, if multiple trig functions set equal to 0 and factor. If multiple trig functions set equal to 0 and factor. If multiple trig functions set equal to 0 and factor. Let's start next to this. Never divide away a trig function. Never divide away a trig function or a trig ratio, if you want to call it that. Never divide away, always set equal to 0 and factor. Because it is tempting. Oh, I can divide a cosine out of everything. No, you're not allowed to divide stuff away. You lose roots, you lose answers. So here, I would need to bring the cosine over class as a negative. But notice, cosine cotangent, like AB, is not a like term to an A. If I bring the A over, that becomes AB minus A, right? It doesn't become like the A, right? It's not a like term. So here, it's going to become cosine theta, cotangent theta, minus cosine theta as a separate term equals 0. Does that make sense? So it said equal to 0 and factor. What can I factor in AB minus A? The A. What can I factor in the cosine cotangent minus cosine? The cosine is the common factor. And when I factor it out, it's going to leave me with
Cotangent theta minus 1.
There we go. And then just like here, we would say set each factor equal to 0. Set x equal to 0 and x negative 3 equal to 0. Remember the premise that if two things multiplied give 0, one of them at least has got to equal to 0. So we're going to do that. We're going to say that the cosine of theta equals 0 and the cotangent of theta minus 1 equals 0. Although, you probably could do this step in your head. What will we do next?
Move the 1 over.
The 1 has to move over to isolate anyway, so we really end up with just cotangent theta equals 1. Just as here, we didn't usually write both of these. We just said x equals 0 and move the 3 over, x equals 3. Right? We usually just jump straight to that. We do the same thing here. Cosine 0, cotangent is move it over 1. Here's the deal. These are ratios. Cosine is a ratio adjacent over hypotenuse. Cotangent is a ratio adjacent over opposite. Make it look like a ratio. Put them over 1 if you have whole numbers. That make sense? Put whole numbers over 1. And then the question is, when is cosine adjacent over hypotenuse 0 over 1?
In the 90-degree triangle.
For the 0, 90, 90, but which angle of the 0, 90, 90
The 90 one.
0.
is the adjacent 0 and the hypotenuse 1?
90.
For the 90. Here's my adjacent of 0. So, I know that my reference angle is a 90 degree. Now here's the deal. Is 0 positive or negative?
Neither.
Neither. Another way to think of it is both. Technically, mathematically, neither, but I want you to assume a built-in, if you will, positive negative for a 0. So we not only want the 90, but we want the negative of 90. Well, here's 90. What would be the negative of 90?
270.
270. So two answers for theta are both 90 and 270. But I've got that other thing over here. Cotangent, adjacent over opposite, is 1 over 1. When would adjacent and opposite both be 1?
0 degrees.
Well, in the 0, 90, 90, the hypotenuse is a 1.
Oh, 90.
We need both legs to be 1.
90.
Think.
The
Both
45,
legs have to be 1.
45, 45.
That's the 45, 45, 90.
Oh.
The legs both have to be 1. So we know the reference angle here is a 45. But here there's not a positive negative, is there? There's just a positive. ASTC, when is cotangent positive? Quadrant 1 and quadrant 3. So I need the 45 degree angle that's in quadrant 1 and the 45 degree angle in quadrant 3. What are those two angles?
45 and 170.
180 plus 45 more in quadrant 3.
225.
225. And this time, there are 4 different answers for theta. Questions on that one? Starting to see the process here. Again, you've got to think what triangle, what angle, and then also what quadrants are we in. With a 0, again, if there's a 0 somewhere in there, it's got to be this triangle. And therefore, if it's this triangle, it's either a 0 or a 90. So it's either 90 and 270 for a positive negative, or 180 and 360. Or 0 and 180, I guess we'd say, since 360 technically is a 0 again. Look at your textbooks at page 140. Page 140. And let's do a couple of these together here. Let's look at number 2. We have a 2 sine squared gamma plus the sine of gamma is equal to 0. Technically, since we have a sine squared, this is a quadratic equation. Does that make sense? If an x squared, we'd say it's quadratic. Well, we don't have x's in this. We have sines and cosines and such. So it's a quadratic. Also, not only do I have an x squared, I have an x to the first. So it's a complete quadratic. Now, for a complete quadratic equation class, we want to set it equal to
0
and factor. It's already set equal to 0. All I have to do is factor.
Pull out sign.
Pull out a sign. Again, don't divide it by sign, but factor out the sign. What am I left with in parentheses now, Jamie?
2 sine, is that gamma?
Gamma.
Yeah. And 1.
Plus 1. And then we need to set both of these factors equal to 0. Well, when I set the sine of gamma equal to 0, I get the sine of gamma equals 0, right? That's not too hard. Here, though, when I set it equal to 0, I'm going to have to do 2 things to get that sign by itself, Ethan.
Divide the 2 away.
Well, not first, because it's attached to the 2, right? That's like my son's baby blanket. We don't want to get rid of that yet. He's not really attached to this 1, though.
Yeah, minus 1.
Let's subtract the 1 over first, then let's go ahead and get rid of the baby blanket.
Alright, so minus 1. And then divide 2, so 1/2.
But minus 1, so negative 1/2. Let me go ahead and show it, because if he...
Oh, yeah, I get it.
He knows it, all right, but he's struggling. There may be somebody watching on YouTube struggling as well, right? We have to move the 1 over to get 2 sine gamma equals negative 1, then divide the 2 away, and that's where we get the sine gamma equals negative 1/2. We're usually really good at doing that in our head, and we will get very good at it again. It's just been a little while, and brain's tired. I did tell you, though, you always want these values to be ratios. So let's put the 0 over, and I told you that anytime you have a 0, you might as well put on a, it's neither, so we can assume it's kind of like both. All right, when is sine, which is what over what?
Opposite over hypotenuse.
Opposite over hypotenuse. When is sine 0 over 1?
0.
At 0. But we have a positive negative, so we need not only the 0, we need the negative of 0.
So 180.
180. So we're going to say here that gamma is both 0 degrees and 180 degrees. We come over here to the sine of gamma is 1/2. When is opposite over hypotenuse 1/2?
30.
Good. The 1 is the opposite for a 30-degree angle. So that's my reference angle, but ASTC, all I've got's a negative. In which quadrants is sine negative?
3 and 4.
3 and 4. So I need a 30-degree angle in quadrant 3 and the 30-degree angle in quadrant 4.
210 and 330.
Good. Coming off the 180, add 30 more. Coming off the 360, take away 30. We get 210 and 330. And there are 1, 2, 3, 4 answers for gamma. Questions on that one? Start to get a feel for these equations. Let's take a look at number 4. This is a fun one. We have 3 is equal to the tangent squared kappa. And this is also quadratic, isn't it? But there's no tangent to the first, so it's incomplete. Do you remember this? Ooh, good algebra review. Incomplete quadratic equation, isolate the x squared, take the square root. Do you remember that? Incomplete, isolate, take the square root. Well, it's already isolated. There's nothing with the tangent squared, so I just take the square root of both sides. And we take the square root of tangent squared kappa class, we get tangent kappa. But when it's your idea to take the square root, you need to make sure there are 2 answers for the square root of 3, which is irrational. So I'm going to leave it as the square root of 3, but positive, negative square root of 3. And I also want it to be written as a ratio, so I put it over 1. Remember the incomplete quadratic with a positive, negative. Now question, when is tangent, which is opposite over adjacent, square root of 3 over 1? 60. That's my reference angle. But ASTC, when is tangent positive and negative?
2 and 4.
In other words, I need quadrants 1, 2, 3, and 4 here. All the 60-degree angles. So, What are my 60-degree angles?
60, 120, 180, 240.
Ooh, you're right about the 60 and the 120.
240.
240
And then 300.
and 300. And there's all four 60-degree angles here because of the positive negative. When you take the square root, positive negative. When you see positive negative, you know you're getting four quadrants. Questions on that one? All right, look at number 6. Oh, we got a, this is appropriate for upcoming Thanksgiving here. We got eta. 3 cosine squared eta minus sine squared eta. Or equals sine squared eta. What did I say? Did I say minus? Equals sine squared eta. I'm thinking ahead a little bit because I have multiple trig functions. And I said, if you have multiple trig functions, class, set it equal to
0
and factor. All right, so I'm going to set it equal to 0. So I was thinking, let's pull the sine squared over as a negative sine squared. At least I'm going to claim I was just a step ahead in my brain already. But, oh, can I factor that? I can't factor that at all. Huh. No, there is a solution.
Difference of squares, so something different.
Well, it's not a difference of squares because we have a 3.
The negative sine squared equals cosine squared minus 1.
Ah, hold on now. This negative sine squared, since I can't factor, could I change it into a cosine squared? And Ethan said sine squared eta, or negative sine squared eta, is the same thing as cosine squared eta minus 1, or positive cosine squared eta minus 1, Pythagorean identity. And so we haven't had to use a whole lot of identities yet, but here's an example where an identity is the only way to solve it. Without the identity, there's no way to do this. But now, it's easy. We've got an incomplete quadratic, but there's a 3 cosine squared and a 1 cosine squared. Let's mush that together.
4 cosine
4 cosine squared. Eta equals 0, right? And it's an incomplete quadratic. So isolate the cosine squared, take the square root. How do I isolate?
Plus the 1 over.
Add the 1,
Divide by 4.
divide the
I was
4,
going to say take the square root of that.
and then,
Take square root.
now that it's isolated, take the square root. But my idea to take the square root,
Positive, negative.
positive, negative, what is the square root of a
2. Or,
a half? Y'all following? All right. All right. Now we're ready. When is cosine adjacent over hypotenuse? 1 over 2.
30.
60.
Adjacent. What is adjacent to the 60? So we got 60. That's my reference angle, right? But positive, negative tells me which quadrants do I need?
All of them.
All of them, because cosine's always either positive or negative, right? So I need all 4 60-degree angles. So what do I get for eta, class?
60, 120, 240, 300.
You read well, Ethan. Smart man,
I mean, who else would?
right? Questions on that? Sometimes you're going to have to use identities to bail you out. When you don't see a path forward, because it's not conventional, you can make it work by using an identity. Question?
You just put that line to separate the answers, right?
Yeah, that was just kind of, it was my way of circling the answers, but it was down at the bottom of the board, so I was too lazy to finish the circle. Yep, good question. All right, let's take a look at number 8. We have the cotangent of omega minus 3 times the tangent of omega, all equal to 0. Multiple trig functions, what am I supposed to do?
Equals 0.
And,
Factor.
well, it's already said equal to 0, so let's go ahead and factor.
Can't factor.
You can't
Make
factor.
it 1 and make the cotangent 1 over tangent.
But let's use an identity, and let's make this 1 over tangent omega. Now, one word of caution. If you create a fraction, you need to be aware that you may be, in the process you're about to use, creating an extraneous root. Take the denominator you create make sure you specify it won't be able to equal 0. Remember, denominators can never equal 0, and if you create a denominator, specify that it won't be 0 and check your answers on that later. Okay, just kind of tuck that thought aside, set it aside for later, we'll come back to it. All right, let's solve.
Cancel a tangent.
Ooh, if I were multiplying, I could cancel a tangent. But do we ever really cancel trig functions? No, that'd be like canceling an x out of an equation. Now you have nothing to solve. What might I do instead? Since I don't like, in fact, I hate fractions in my equations. Multiply everything by the LCD. You remember that? So you're going to multiply everything by the LCD. And this is the reason why extraneous roots could be created, is because you're multiplying an extra tangent into everything. So that's why we may have to check these answers here. Here, of course, the tangents are going to cancel, which is acceptable, okay, because we're not canceling with something else there. We're artificially canceling to get rid of the fraction. Here, we have a negative tangent times 3 tangent. We're multiplying negative 3 tangent squared omega, and tangent times 0. Zero. And all of a sudden now, we've artificially made this a quadratic. It didn't look like a quadratic to start with. We've made it a quadratic. And so, again, that's the reason why there's the chance we could have extraneous roots here. But we're just solving here. It's an incomplete quadratic. What should I do?
Subtract the 1 over.
Divide by -3. Take square root.
So we have the tangent of omega equals, and when I take the square root, I can't take the square root of a negative, but it's already a positive, right? So what do I get for the square root of 1/3? Well, normally we'd have to rationalize this, right? I would not. I would take the square root of 1 to get 1. I would leave the square root of 3 as the square root of 3 in the denominator, because it's not an answer. It's a way of getting the answer. And don't forget your positive negative, because you put that square root symbol there. Questions? Did I lose anybody? We're all good?
Okay, so, how did the square root of 1 over 3 turn into 1 over 3?
Well, because, like, for instance, if I have the square root of 4/9, you can take the square root of 4 to get 2, and the square root of 9 to get 3. If I have the square root of 7/25, I can take the square root of 25 to get 5, but I can't take the square root of 7, so I'll leave that. If I had the square root of 3/4, I'd have to leave the square root of 3, but I can take the square root of 4. Well, you could technically do the same thing here. I take the square root of 1 to get 1, but since I can't take the square root of 3, I just leave it. Normally, we wouldn't do that, because normally in an answer, we never leave a radical on the bottom, but this isn't an answer. It's a means of getting the answer. And it's going to help you if you don't rationalize, because this way, when is the opposite 1 and the adjacent square root of 3? 30 degrees. And we got a positive negative, which means I want all 4 quadrants. So what are my 4 omega answers?
30, 150, 210, and 330.
There we go. But one thing we got to check. We got to make sure that the tangent of these, none of them ends up coming to a 0, right? Well, if you want to on your calculator, you could check here. Is the tangent of 30 0? No. What about the tangent of 150?
No.
210?
No.
330?
No.
Okay, we're good. Don't get complacent though, because about the time you're like, I'm not going to bother, that's when it's going to bite you, okay? But no, none of them happen to come out to a 0 if you take their tangent, so we're good. But something to watch for there. Questions on that one? All right, let's take a look at number 7 now. We've got the sine row minus 1 times 2 cosine row positive square root of 3 all equal to 0. And a lot of students look at that, ooh, we can FOIL. Wait a second. Do we have multiple trig functions?
Yes.
Yeah. What do I want to do when I have multiple trig functions?
Set it equals 0 and factor.
Set it equal to 0, like that, and factor like that? In other words, they already did all the hard work for you, okay? Don't mess it up by trying to FOIL this. They've already set it equal to 0, they've already factored. Just take each factor and set each one equal to 0. So here I'm going to get that the sine of rho is equal to 1. Be careful here, the cosine of rho is going to equal
Negative square root of 3 over 2.
Negative square root of 3 divided by the 2. When you move the square root of 3 over as a negative and divide the 2 away. I will want to make sure that I put this 1 over 1. And what sign, what SIGN does it have?
Positive.
Positive. Questions on that so far? Anyone feeling lost?
No, I was just, doesn't he leave for the,
Oh yeah, thanks.
Well, maybe this one?
No, that's next hour. That's next hour. He
Alright,
gets, yeah, never mind. I do have a note about it, but that's next hour. He's got to
What
leave.
time is that anyway?
11:40.
Alright.
All right. So we ask ourselves, selves, when is sine opposite over hypotenuse 1 over 1?
90.
1 over 1.
90.
90. All right, but notice it's only the positive. So I'm only going to have the 90 degrees, not the 270 also. 0 has a positive, negative. 1 doesn't. It's just plain positive. All right, let's come over here. Negative square root of 3 over 2. When is cosine adjacent over hypotenuse
30 degrees.
square root of 3 over 2?
Yeah, 30.
At 30 degrees. But negative, when is cosine negative?
1.
2 and 3.
Yeah, 2 and 3.
So I need the 30 that's in 2 and 3.
150
And 210.
And it doesn't happen often that you get an odd number of answers, but we do have an odd number of answers. 3 answers that would satisfy the equation. Questions on that one? Let's take a look at the next page. I think we have time for just one more here. Number 9 kind of has an unusual twist to it. 2 square root of 3 cosine mu equals square root of 6. It's actually a really easy first step. What should we do?
equals 0. Or no.
Divide the 2 away.
Yeah.
And
Square root 3.
divide away the 2 square root of 3, because that's what's being multiplied by cosine. Now, when you do this, quick refresher on dividing radicals, you divide the coefficients. What's 1 divided by 2?
1/2.
A half. And you divide the radicands. Square root of 6 divided by square root of 3 becomes
3.
square root of 2. Square root of 6 divided by square root of 3 is square root of 2. Which, normally, I would not write this 1/2 square root of 2. How's the normal way to write this?
Square root of 2.
Notice it's already positive. When is cosine adjacent over hypotenuse square root of 2 over 2?
45.
We should have memorized this 45. Technically, it would be 1 over square root of 2, but we've seen this so many times rationalized. We know it's 45. Positive, though. When's cosine positive?
First and
First and fourth. So I need the 45 in 1 and the 45 in 4.
So 45 and
350.
350. Or 15.
And there's my angles. Questions on that one? All right. There is no homework this evening.
I like that.
We'll continue working with these more in our next lesson. Any questions before we wrap it up? All right. We'll have a wonderful rest of your day when the bell rings. You'll be dismissed.